Okay, time for another question. This is about dot cross diagrams for covalent compound. A molecule of ethanoic acid. So a molecule means it's covalent. And here's the structure showing the covalent bonds. So you've got double bond there, and the rest of them are single bonds. And then you have to convert that into a dot cross diagram. Now, surprisingly, it doesn't happen very often, but they haven't given a key, okay, what symbols to use for the electrons of which atoms. So in this case, you're going to have to make a key yourself. The other important thing about the key, and I've seen loads of students time and time again make this mistake, they say that the symbol that they've chosen equals oxygen, not the oxygen electron, or they say oxygen atom, and it's not. Okay, it's very important. It's a serious mistake. Oxygen is not the same as an electron from oxygen. Okay, otherwise it means something completely different. So anyway, make sure you get the key right. You can start pretty much anywhere. I like to start with the single bonds with the hydrogens. So the symbol for the hydrogen electron was a cross. Hydrogen only has one outer electron, and that's being used in bonding here. So fill all the hydrogen electrons in. Okay, remember these overlapping areas are where the actual covalent bonding takes place. That's where the electrons are being shared by the two overlapping atoms involved. So one electron from hydrogen, and then we can put the carbon electrons in, and according to the key we used the circle for the carbon electron. So the carbon returns the favor in a single bond. Remember, one pair of electrons is being shared. That's one electron from each atom, two electrons altogether in the bond, or one pair. Okay, and it's equal sharing, in this type of covalent bonding. Another single bond here between the two carbons. So this carbon puts one electron in, and this carbon puts another electron in, and they share one each. And then here, carbon. Now this one is a double bond. Okay, this one is a double bond. So that means two electrons are being shared by each atom. You can refer back to the structure. There you can see carbon-oxygen double bond. So the oxygen returns the favor and also contributes two electrons. Now it doesn't matter how you draw those electrons in here. So for example, you could draw them like this, next to each other, and so on and so forth. Okay, as long as you draw them in that shared region. So two from the oxygen and two from the carbon. That's your double bond there. And then here it's a single bond, so one from each, and obviously it returns the favor here by also sharing one electron back with the hydrogen electron there. Now the last thing is to check the number of non-bonding electrons. All the bonding electrons have been done. Now the non-bonding electrons, oxygen, remember, has got 6 outer electrons. It's in group 6. It's got 6 outer electrons. So out of those 6, so far we've used up 2. So how many has it got left? 4. So those 4 non-bonding electrons are shown away from and outside of the shared region. Okay, anywhere in that non-bonding region. And likewise, this oxygen, out of the 6 outer electrons, it's used up 1, 2, so it's got 4 left. 1, 2, 3, 4. Hydrogens obviously don't have any electrons left over. They only have that 1 electron, and they've used it up already in sharing in the covalent bonds. Carbon likewise has got 4 outer electrons, so this carbon is used up 1, 2, 3, 4 already, and this carbon has used up 1, 2, 3, 4 already, so they have no non-bonding electrons left. It's also useful to do a quick double check at the end by counting up the total number of electrons around each atom, which should be 8 according to the octet rule, apart from hydrogen, because it only has the first energy level filled with electrons, making it 2 around each hydrogen, but 8 around the rest of them. So in this case, 8 electrons in total around the carbons, and also 8 in total around the oxygens.